Alright, so I wanted to take a moment to go over this practice test and just give a breakdown. You could feel free to put it at double pace or jump around to certain questions. I'll try to move with relative clarity and quickness. So, first question, just to highlight also, a lot of these questions are the same as the activity that we had done on Monday, yesterday, which was the 14th. So, solve the inequality and the equation of the exact same format, just a different sign. Describe the similarities and differences. So here we've got 5 square root of x minus 3 minus 2 was less than or equal to 13. Then we've got the exact same structure except for a change from a less than or equal to sign to an equal sign. So in solving these two equations, what you'll notice, I would get 5 root x minus 3 equals 15, divide by 5. So square both sides, add 3, x would equal 12. If I go through those same steps, I would end up with the same thing here because they're the exact same structure. But I would have x is less than or equal to 12. What I need to now do, and this is the difference in the two, is consider the radicand. Are there any limits that I need to add here on this answer set of x is less than or equal to 12 that would cause a problem given my radicand? Well, I know that a square root cannot have a radicand, that is negative. Or we know that, for instance, this radicand must be greater than or equal to 0. So if I solve for x, I know that x has to be greater than or equal to 3, which if I am to invert it, would give me this compound inequality there. So that's the difference in my process, is this considering of the radicand and limitations on the domain that come from, especially an even root. It wouldn't matter if this were greater than 12 because there's no issues with numbers greater than 12 with the radicand, even of an even root. Or if this were an odd root and still less than, we can take the odd root of negative, so there would be no issues there. So that's number one. Number two here, so describe the transformation. Well, you see, this is a good hint for stretches or shrinks. If the square root, right, the square root of 1 is 1. So we see that it doesn't seem to be stretched or shrunk, because if you go over 1 and up 1 from this, I guess sort of the vertex, I don't know if we're allowed to call it that, but it looks as though this is simply a transformation, is a translation, right, 1, 2, 3 units. And that seems to be the only. And so we could then say my rule g of x, well, how would I translate 3 units to the right? Counterintuitive, so I subtract 3 on the input. Okay, this one, so I know originally my cube root of x usually goes like this, right? Oops, that was very incorrectly drawn. Oops. Let me try that again. So it's usually like this. So what we can see here is, once again, this has been stretched. Instead of going just over 1 and up 1, and it's been reflected. So it's a stretch vertically by factor of 2, because instead of going 1 over and up 1, and it's a reflection, wow, over the, well, it could be the x or the y-axis. We could just call it the y-axis, or sorry, a vertical reflection, because if you have a, which would be about the x-axis, because I think because algebraically, if we have a negative 1 underneath here, we could always take the cube root out, because the cube root of negative 1 is still negative 1. So my rule g of x in this case would be just I could put the negative in front and the 2 in front to make them both vertical transformations. And then my last one here is a fifth root. Once again, we don't see it going through this point here. And it looks as though it's been displaced. So this is a stretch, a vertical stretch by a factor of 2 again. And a translation up 2 units. So g of x in this case would be vertical stretch, so add a 2 in here to my fifth root. And then the translation up 2 units would come afterwards. Okay, not too bad so far. Okay, explain my reasoning. This is a tricky one, but I know the denominator is the root and the numerator. And actually 64 is a perfect cube of 4 because 4 times 4 times 4 is 64. So I could rewrite it as this, 64 to the 1/3 to the second. And that would be 4 squared, which is 16. Okay. Once again here, 27 and negative 27 are perfect cubes. So I could attack it this way. It doesn't say no calculator on these, which is a little silly, I guess. But I would get negative 3 to the 5th, because the cube root of negative 27 is negative 3. So that'll give me negative 3, positive 9, negative 27, positive 81, negative 243. Okay. The next one here, I need to see, are there any fourth roots that could be taken out of this radical? Let's take a look-see here. Well, 48 actually has 16 as a factor. And y to the 11th, well, we're looking for the multiple of 4 that is the greatest multiple of 4 that is less than 11, because 11 itself is not a multiple of 4. So we could rewrite it as the fourth root of 16 times 3. We still have this x. And then we could break the y to the 11th to y to the 8th times y to the 3rd. And extend this. So now the 16 and the y to the 8th are the only aspect, or the only components that I can take a fourth root of. So 2 is the fourth root of 16, and y squared is the fourth root of y to the 8th. So I still then have all of this remaining, 3x y cubed z cubed. And that's as far as I can go, because none of these have perfect fourth roots, or fourth power factors. Okay, 256 over 32. Well, actually, I believe I could rewrite this as the cube root of the quotient, which is just the cube root of 8, and the cube root of 8 is indeed 2. Okay, now we're cruising. Write two functions whose graphs are translations of the graph of y equals root x. The first function should have a domain of x is greater than or equal to 4, and the second function should have a range of y is greater than or equal to negative 2. Well, we know originally a square root function, if I draw it in red here, has a domain of x is greater than or equal to 0, and a range of y is greater than or equal to 0. So, this first example, for this domain to be possible, I would just have to shift this graph 4 units to the right. We could call it g of x, and an easy way to shift it 4 units to the right would just be to subtract 4 in the radicand. Now let's try one. Well, for it to have a range of greater than or equal to negative 2, we could call this h of x. We would have to shift it down 2 units, which is just going to be minus 2 outside of the radical. Wow, not too bad. So for everybody who likes to play bowling or golf, This question talks about the concept of a handicap. So in bowling, a handicap is a change in score to adjust for differences in the abilities of players. So if you're a really strong player, you would have a very small handicap, I believe. Correct me if I'm wrong. So if you belong to a bowling league, they have this formula where the handicap is determined using the formula the handicap equals 0.9 times 200 minus A, where A is your average score. They're asking us to find the inverse of the model. So basically a model that could find your average score given the handicap, since this is telling you the handicap given the average score. So let's do this systematically. Remember we said we're actually going to be doing ourselves a favor every time we actually do this systematically, and often it's the most efficient and effective way to do it. So in this case we want to solve for A in terms of H. So first I'll have to either divide by 0.9, or you could also, we could do that. But you could also think of 0.9 as 9/10 and multiply by the reciprocal times 10 over 9 if you like, because that's what 9/10 is, a fraction. So I get 10h over 9 equals 200 minus A. What I now could do is subtract the 200. But that's going to equal negative A, so I could multiply everything by a negative and move my A on the left side, and I would get negative 10h over 9 plus 200. So I guess the textbook didn't have this as sophisticated as we did. They had it as 200 minus h over 0.9, which is equivalent to what we have here. So because you can multiply by the reciprocal to get this. So either answer is good. So now it's saying use your equation to calculate the average for a bowler whose handicap is, what was it, 36? So now that we have this equation, we could find the average in a quite straightforward manner by just saying, okay, the average. So this per bowler with a 36-point handicap, there she goes again, acting funny. Gotta fix my OneNote here. Divided by 9 plus 200. So this becomes, 36 over 9 is 4. That's nice. So negative 40 plus 200. So my average would be, what am I talking about? 160. That would be somebody's average score, which I think sounds good to me. I'm just an amateur bowler, but maybe in the professional realm, I don't know. So I believe 160 would be that person's average score given their 36-point handicap. Alright, the basal metabolic rate of an animal is a measure of the amount of calories burned at rest for basic functioning. Kleber's law states that an animal's basal metabolic rate in kilocalories per day can be modeled by this rational exponential equation, where W is the mass in kilograms of the animal. Find it for each animal here. So this is one where we would use our calculator. And I think it's mostly assessing our ability to evaluate rational exponents. So here we've got the mass in kilograms, so I don't think we need to do any unit conversion here. Always good to double check. So we could just say, the one option is we could just go through and do it for each value, 73 point, oh no, it's not letting me